projection. What do we mean by projection in a linear algebra? So basically, whenever we have two subspaces whose direct sum is given a vector space, then we can define a projection from x to x1 or x to x2. So because we have a unique representation, every x we can represent as a sum of two elements using the direct sum decomposition. So here we have discussed the projection on the first component, that is on x1. So that is a linear map, and not only it is a linear map, it satisfies this special property, which is the definition of projection in linear algebra. So example we discuss is R2 we can write as a direct sum of x-axis and y-axis. And here again we discuss projection on the x-axis, but similarly we can discuss projection on y-axis. When we take projection on x-axis, the kernel of the map is basically y-axis. In this case, we say that this particular map is a projection of R2 on x-axis along the y-axis. So basically it is along the kernel, and kernel here is the y-axis. So then we discuss the definition of partial order set. Any set which has any relation which is antisymmetric, transitive, and reflexive is called partial order relation. A set along with partial order relation is called partially ordered set. And we discuss example. First example is over natural numbers. M divides n is a partial order relation. Similarly, if we have any non-empty set, then the power set is also a partially ordered set with respect to this relation A subset B. Okay, and then we discuss the definition of upper bound with respect to partial order relation and maximal element. And Zorn's lemma says that, and we discuss this definition of chain. The chain means any two elements in that set, either x will be less than equals to y or y will be less than equals to x. So you choose any two elements, this is always satisfied for those two elements. So some example we have seen here, and this is my axiom which is called Zorn's lemma, which says that every non-empty partially ordered set in which every chain has an upper bound, then it has a maximal element. So this we are going to apply in the first result which we are discussing now, that if we have a vector space over a field K, and suppose L is a linearly independent subset of X, and S is the spanning subset of X. So spanning means its linear combination is the whole vector space. So such a set is called spanning subset of X. So if we have a linearly independent subset which is contained in the spanning set, then we can find a basis which lies in between them. That is what we want to prove. So to prove that, first of all, we need a partial order relation. So we are considering the collection of all such sets which lies in between L and S, which is Li. So it is a subset of power set of X. So we can define a partial order relation subset on this family, and so this is a family in which the elements are sets. And in this family E, we are considering the chain, any arbitrary chain F. So for this arbitrary chain F, as many elements F is there, we are taking union of all those sets, and we are forming the set E0. And we can see that if every set F satisfies this property, then union also satisfies this property, and therefore E0 is between L and S. Right? E0 contains L and E0 is subset of S. So basically E0 is maximal element, is an upper bound of F, and on the other hand we observe that E0 is Li, right, because of the chain condition. So let us note down that E0 is a Li subset as well as, so E0 is Li means what? E0 is Li as well as it satisfies this condition. So that means E0 is an element of E. What is E? E is the sets which satisfy this property as well as it is Li. So E0 satisfies both of these property. That means E0 is an element of E. So note that E0 is an element of E. Right. So that is because E0 is Li and E0 is a L subset of E0 subset of S. So now E0 is in E, and E0 is a union of all elements of F. Right. So that means what? That means E0 is a upper bound for F in E. So E0 is an element of the partial order set, and it is bigger than equals to all elements of F. Right? Why? Because F is a subset of E0 for all F in F. So this is the condition of the upper bound. Right? What is the condition of upper bound? X should be less than equals to Y for every X in the subset. Here subset is this chain, and E0 contains each F because it is a union of all F. Right? So it is a maximal element. It is an upper bound. So so the condition of Zorn's lemma is satisfied. So therefore, by Zorn's lemma, so what is Zorn's lemma? Zorn's lemma says that if you have a partially ordered set in which every chain has a upper bound, then the partially ordered set has a maximal element. So by Zorn's lemma, so if we apply Zorn's lemma, what we get? So what is the partially ordered set X in this proposition? Yes, Gaurav. Yes, Gaurav. Am I audible? Yes.
Yes, sir, you're audible.
Yeah. So what is the partially ordered set we are considering in this example, in this result? So here, what is the partially ordered set?
subset.
Yes. Yeah, what did you say?
E.
E, right. So E is a partially ordered set, and in which what we are taking, F is a chain. F is a totally ordered chain, right? That is a subset of E. So if we apply this Zone's lemma, then what we get here, basically instead of X in this result, we have E, and in which we have totally ordered subset which we are considering is uh, subset is F, right? F of E. Then every totally subset F of E has an upper bound that we have verified. So finally what we get, E has a maximal element, right? So that we are getting from the proposition. So let us write down that by Zone's lemma, in since each totally ordered set F has an upper bound in E has a by Zone's lemma, E has a maximal element, right? So that is what we are getting from the Zone's lemma. So let us call this element, we will denote it by B. So we denote this maximal element by B. So now we got the maximal element. So what does uh, this element? This element belongs to E, right? Because it is a maximal element of E. So since B belongs to E, what we get? B is Li, right? By the definition of the family E, B is Li, and what we know is B is in between L and S, right? So this is what we get from the as a because the maximal element exists in E, right? E has a maximal element, so that means B belongs to E, and by the definition of elements of E, B is Li, and L is a subset of B subset of S. Now our claim is that this maximal element B is a basis for given linearly independent set X, right? What is X? X is the linearly independent set from which we started. X is a vector space. So we are searching for the basis B. So basis means we know that there are two properties. First property is B is Li, and second property is B spans X. Right? B is the spanning subset of X. The first property we got from this, that B is Li because it is element of E. But the second property we need to check the basis, right? So to check B is a basis, we need to show that B is a spanning subset of X, right? So this is the only thing we need to check because we already got that B is Li. So now to check this, let us assume that this is not true, right? So basically to show that span of B is X, and what we know is we know that we have a spanning subset of X. So in the statement itself, it is given that there exists a set S whose span is X. So if we can show that S is a subset of span of B, right? So if S is a subset of span of B, then span of S is a subset of span B, which is subset of X, and span of S is X. So that means we get span of B is X, right? So if this we can show, then we will get that B spans X, right? Using this property. So what we do is we will assume that this is false, and then we will get a contradiction. So that means this is correct, right? So suppose S is not subset of span of B, right? So that means what? That means that this statement fails means there exists some element which is not in this. Uh, there is some element in S which is not in span of B, right? There exists X belongs to S such that X is not in span B. Because if every element of S is in span of B, then S will be subset of B. Okay, so now we got an element which is not in the span. So this thing we used earlier also, right? So if we have an element which is not in the span, then what can we say about that element? If we add that element, then the new set will also be
Linearly independent.
linearly independent, right? So basically we are using B is a linearly independent also. So therefore X union B is linearly, just a minute, independent. Okay, so why this is true? Because we already know that B is Li, right? And X is not in the span, so that means when we add this, we get a Li subset. But now what we got? We got this is a larger subset than B. So, so in fact, we can, if you recall the proof, why this is a Li. So if we want to show this, what we take, let x1, x2, xn are elements of B. So if we take any linear combination, is 0, we want to show that this set is Li. So if you take any linear combination is 0, Then what we get is we get kx is equals to minus k1 x1, k2 x2, kn xn, right? And what is this? This is belongs to span of B because x1, x2, xn is in B. So that will give us kx is element of span B, but we know that x is not element of span B, right? X is not element of span B, so that will give us k is 0, right? Because if k is non-zero, then you can multiply by inverse of k, and that will give us x belongs to span B. So we got k is 0, and if we substitute k is equals to 0 again in this equation, we get k1 x1 plus k2 x2 plus kn xn is 0, right? And that will give us k1 k2 kn is 0. So that will give us k is equals to k1 k2 kn is 0, and therefore the set x x1 xn is li. So therefore basically x union b is li, right? So basically we are using here the result of linear algebra, and proof is basically in the bracket. We have verified that. So essentially what we got is therefore we got a bigger set B union X is Li, and L is a subset of B subset of S. So what we get is this gives what can we say about B union X, whether B union X satisfies this property. So clearly L is a subset of B and B is a subset of B union X. So we can say this one, right? And on the other hand, what can we say? Whether this is a subset of S. So what do we know about the relation in between B and S? We know that B is a subset of S, right? And what else we know is X is also element of S, right? So if B is a subset of X, B is a subset of S, and X is an element of S, then clearly B union X is a subset of S, right? Because both of these is a subset of S, so its union is also subset of S. So finally, what we get is therefore B union X is a Li is a linearly independent subset of what? Subset of X such that L is subset of B union X subset of S, and B contains B union X, and this cannot be same. It is a proper subset. Why? Because X is not element of B. That is what we assumed here. X is a not element of B, right? So B is a set which satisfies this property, as well as B union X also satisfies this property, and B union X is a bigger than B with respect to the partial order relation. So what does this means? This means therefore B is not maximal. Right. So what is maximal? Maximal means if we have an element which is maximal, then x less than equals to y implies x equals to y. So here the relation is subset relation. So B is maximal means if we take any subset which is contains B, then it must be equals to C, right? For this particular partial order relation. But this is not true because we are getting the set B union singleton X, which is bigger than B, and that is not same as B, right? B is not equals to B union X. So therefore we are getting a contradiction that B is not maximal, which is a contradiction. So this contradiction arises from our assumption, our wrong assumption, and the wrong assumption is that this one, S is subset of B is false. So therefore S is a subset of span B. Right. So our assumption was wrong. We got the conclusion that S is a subset of B, and if S is subset of B, then we already observed that span of B is X. So therefore, whatever B set we got, which is a maximal set, that set is a basis of X. Right. So this proof will give us a corollary which we can use to find every basis. We get to find a basis for a vector space. So let us write down the corollary. So let X be a vector space over K, and in which there exists a basis for X. That is what we want to prove as a first result. Second result we want to show is that if Y is a subspace of X, and C is a basis for Y, right? C is the basis for the subspace, then we can find a basis for the vector space such that C contains B. C is contained in B. Just a minute. So basically we can expand the basis of the subspace to get the basis of the vector space. That is the second part. So let us prove this. So first part says that for every vector space we have a basis. So we want to apply this proposition essentially. So what is the statement of the proposition that says that if we have a vector space in which we have a L and S, then we can find B such that L subset B subset S. Right. So to find the basis B of X, we need to choose L and S. Right. First of all. So to find basis for given vector space X, we choose. So can you give a simplest Li set in any vector space? Yes, Jayesh.
So what is the question?
We have any vector space.
Hmm.
Then what is the simplest linearly independent set in that vector space?
So the zero set.
Zero
मतलब
is,
जो उसका basis जो उसका निकालेंगे like the one that the spanning set is the smallest subset is the spanning set, smallest subspace.
see, again I'm asking the question. If you have a vector space, right? What is the simplest linearly independent set in that vector space? You take some example if you want. R3.
So the standard basis if we take
Yeah, but that is
R3.
that has three elements. Suppose we
Hmm.
want only one element.
Yeah.
So can we
Uh,
say that every non-zero vector?
smallest Li set you are asking, na?
Yeah, smallest, right?
Yeah.
So
So
if you take just a singleton set,
1 0 1 1 1.
yeah.
1 0 0.
So to take, so since to find a basis for this, we are taking L is equals to X, where X is any non-zero vector in X, right? Whatever vector space we take, non-trivial vector space, that means it has at least one element other than zero, right? You can choose here non-trivial vector space, not non-trivial. That means it has at least one non-zero vector, and we know that if we take singleton set, which is non-zero vector, and that is always Li set, right? So L we have chosen here. Now, what can we say about S? So what is the simplest spanning set in every vector space? Can we take the whole vector space itself? So does R3 span R3? Yes or no?
Yes, sir.
Span, right? So
Yes.
that means the spanning set is also simple to choose. So what we know is this: This set is Li, the other set is spanning set, and therefore by the proposition in the previous proposition, there exists a basis B such that this basis contains L. So L is the singleton set and it is a subset of X. It is subset of S, but S is X. We always get a basis which contains a particular element. So this result we already know in finite dimensional case, that if we are given any non-zero vector, we can always expand it to the basis, right? But in infinite dimensional, this is a non-trivial thing. So therefore, we are proving it using this proposition. So again, we are not saying that basis is unique. We are only saying that there exists a basis. Right? So in general, that can be more than one basis also in infinite dimensional case. And also, we are not explicitly saying what is a basis. Right? Only we are saying that exists a basis. So this is the existential result. It doesn't give basis. Okay, so now second part is that if we have a basis of the subspace, so that means C is the basis of the subspace, so itself is Li, so we can take L is equals to C, right? And again here also we will take S is equals to X. What is C? C is the basis of the subspace. If we apply this and using previous proposition, we get a basis B so B of X, right? C was the basis of Y, but B is now basis of the vector space X, such that C is subset of B, which is a subset of X. So therefore, we are getting a subspace, a basis which is a having the each elements of the basis of Y. So that is what we wanted. We want a basis which contains C. Okay, so this is regarding the existence of basis in the infinite dimensional infinite dimensional vector space. Now, one example we want to discuss today is regarding the functionals. So we discussed that if we have a linear map whose codomain is one dimensional, then such a map is called linear functionals. So linear functionals are useful to study dual spaces. So if you have a vector space, if you want to study its dual space, then we study functionals. So let X and Y be finite dimensional. Finite dimensional. So the vector space. Let us fix the basis also. The vector space is with basis of X is x1, x2, xn. And basis of Y is y1, y2, yn. So that means X is n-dimensional vector space, Y is m-dimensional vector space, and we know that if we have any element of X, then X we can write in terms of the basis elements. So that is a1x1 plus a2x2 plus anxn, where this a1, a2, an are called coordinates of X with respect to x1, x2, xn. So if you take R with standard basis, Rn with standard basis e1, e2, en, then basically this a1, a2, an are coordinates in the usual sense. But in general, we can write coordinates with respect to any basis for each j between 1 and n. Define functional. So we are defining fj from x to k. So fj function we are defining on each element of x as aj. Right? What is aj? Aj is this jth coordinate. So basically f1 is a1, f1x is a1, f2x is a2, fnx is an. Right? So these are basically the coordinate functions. Also, we can say that, and moreover, they satisfies fjx is equals to aj. Sorry, fjxi is equals to delta ij. So what we are doing here basically is that, yeah. So what is delta ij? Delta ij is the Kronecker symbol. That is 1 if I is equals to j. It is 0 if I is not equals to j. So whenever we apply fj on x1, let us see what happens. So basically the jth coordinate of x1, but in x1 there is no jth coordinate, right? Because if x1 as a combination of x1, x2, xn, then we only get a combination is x1 times x1, right? There is no jth coordinate. Right. So therefore, fjxi we get as a delta ia, and in this case we can write x, which is a1 x1 plus a2 x2 an xn. What is aj? Aj is fj x. So that means this is f1x x1, f2x x2, fnx xn. Right. So x we can write in this form using the coordinate functions, and similarly for, so far we use only x is n dimensional, right? But we are also given y is m dimensional. So the same thing we can do for vector space y also. So similarly for each I in 1 to m, we can define gi from y to k by, now gi we are defining on yj, that is delta ij, for every j in 1 to up to m, and this is coming from the definition that gjy is basically phi, right? So we have these both properties, and therefore we get y is equals to g1y, y1, g2y, y2, gmy, ym. Right, so we get a combination of vector y as a function of g1, g2, gn. Why we need this? Because we know that if we have any matrix, then corresponding to the matrix we can write down find out a linear transformation. So consider an m cross n matrix aij, right, and where kij entry belongs to k. So here I is the element between 1 to m, k is the element between 1 to m, right, because it is a k cross n matrix, m cross n matrix. So for each x, we know that we can write x as f1x x1 plus f2x x2 we consider the corresponding y, which is summation 1 to m summation 1 to n aij fj ya. So how we are getting y is coming from here. So for example, if we multiply this matrix, which is k11, k12, k1n, k21, k22, k2n, and the last row is km1, km2, kmn. So this we are multiplying with the coordinate of x. So that is f1x, f2x, fnx. Right, because each row has n entries, we can multiply these two matrices, and finally when we multiply we get summation j1 to n aij fj x. Right, so this we are defining as ith coordinate of y, because it depends on I also, right? For each I we get this summation. So this we call giy, and if we take g is this is giy, then we know that y is equals to summation I giy yi, right? So just now substitute this here, so we get summation j1 to n aij fj x yi. So that is exactly this number, this vector. Right. So corresponding to x, we have the coordinates of x, and for given matrix M, we can find coordinates of y. So that means from x, we are finding y using this matrix. So what we have done is we have defined a map f from x to y by fx is equals to y, this particular y, for every I is in 1 to m and j is in 1 to n. We get gi of fxj. So what is the ith coordinate of fxj? So fxj means we know that if we take xj, then we get only jth function, right? Depending on which xj we are taking. And when we apply capital F, that means essentially we get the, so basically what element we get corresponding to xj. So if you take xj, all the other case will be 0 except that jth term. So that means this term will be only aij. So this you can verify later on also. That is directly coming from the definition itself. What it says is that gi is what? Gi is the ith coordinate of the yth vector. Ith coordinate of y is this entry, ith entry. And note that f is linear. So that we can easily check. So what we got is given matrix, we have defined a linear transformation, right? The converse we'll discuss in the next lecture tomorrow. So let me stop here.